to this week's webinar, Alarm Rationalization, the Key to an Effective Alarm System. My name is Todd Stauffer. I'm the Director of Alarm Management here at Exida and Product Manager for a tool called SILAlarm, which is a tool for alarm rationalization. I've been involved with alarm management for over 15 years, recently with the ISA 18 committee in the development and approval for the ISA 18.2 standard, which we will talk a bit about. I've also dedicated myself to fixing the alarm management problems that I caused when I was a configuration engineer. So a lot of the lessons that we'll talk about today, hopefully we'll be able to relate to real life practices that you all have seen and done in the past. So a little bit about Exida. We were founded back in 1999 with a vision of making the world a safer place, primarily process plants. And that vision has expanded in the last few years to include alarm management and cybersecurity, other things that are important to keep process plants safe. Initially, the focus was primarily on process safety and kind of all elements of it, from the certification of devices for use in safety instrumented system, as well as the education and certification of people to be competent in doing safety calculations, safety instrumented system calculations and design. So we also have a suite of tools for safety instrumented system design, which includes, amongst other things, our SILAlarm alarm rationalization tool. So what we will talk about today, a little bit about alarm management standards, including what an alarm is supposed to be, and then we'll focus on alarm rationalization with the what, why, where, how, who, pretty much everything related to rationalization. Who should take part, when should it be done, what's the process, why are we doing it, what's the benefits. We'll talk about some of the best practices along the way, the things to think about, the things to document, the things to consider, how we determine whether an alarm is actually necessary or not. And we'll use the SILAlarm tool as a basis of demonstration for an example problem. So I will go back and forth between the PowerPoint slides and the product demonstration. So first let's talk about alarm management and common alarm management issues. The operators in a typical process plant have a significant impact on the productivity and financial bottom line of a plant in the decisions that they make. Now, to make the operator as effective as possible, one of the tools at their disposal is the alarm management system. A good alarm management system only communicates to the operator when their attention is really needed and they need to do something. A bad alarm management system cries wolf. It actually sends messages to them that they don't need to know about or don't need to respond to, which actually gets in the way of them doing their job and makes it harder for them to do their job. So if you work in a plant that has any of these alarm management issues, operators getting too many alarms, whether it's a steady state scenario or a transient, getting nuisance alarms, meaning alarms that occur that don't go away even if the operator takes the correct response. And there's different types of nuisance alarms. Maybe there's alarms that they know they don't even need to respond to. Alarms aren't prioritized correctly, or maybe there's a poor management of change with individual operators being able to change settings from one shift to another. So if you've got any of these issues, there's an opportunity for improvement to make the system work better and to thus help the operator improve their performance. And the key way to do this is through a process called alarm rationalization, which is what we're going to talk about. So first, let's talk a little bit about how we got into this situation with all of these alarm management problems. If we think about the olden days in a typical control room, it was run by panel board control. So there was a limited amount of space actually on the walls for the panel board alarms to be displayed. So there was only a certain number of alarms that could be set up. So you better believe that there was a lot of thought put into what alarm should actually be set up, what alarm should be configured, because there was limited space and there was a real cost to actually wire them up. Fast forward to today, the modern DCS isn't technology great. It's actually taken things in the reverse direction. We tend to treat alarms as if they are free and don't give them a lot of thought as to whether we actually need them. So what happens is we end up with too many alarms that we don't need, which get in the way of the operator doing their job. So a typical DCS provides you with the option of enabling a high, a low, low, a deviation of rate of change. There's a ton of different alarms that can be enabled for each individual signal. And in a lot of cases, if folks aren't sure whether they need an alarm or not, what they're likely to do is enable it just in case. And that is what contributes to the problems that we have today. So what we want to do is get back to the thought process that used to be used, where we justified the need for the alarm. Because we had limited space, we had to go through a process to determine, what was the real purpose of the alarm? What's the operator supposed to do when that alarm occurs? And that is the rationalization process. That process is called out in the alarm management standards. In the US, the pertinent standard is called ISA 18.2, came out in 2009 and is actually being updated, will be released again in the next probably 3 to 6 months. There is also an international standard called IEC 62682, which was released last October. It was developed from the ISA 18.2 standard as a starting point. So the two standards are and what they advocate. They both talk about something called an alarm management lifecycle, which is really a work process for executing an effective alarm management program. And contained in the alarm management lifecycle is a stage called rationalization. Now, the other thing that these standards do very well is kind of define a common set of terminology to be used throughout industry and amongst users. One of the most important terms and concept is the definition of what an alarm is, or what it's supposed to be, and that is an audible and/or visual means of indicating to the operator, and in this case I've underlined the word operator to reinforce that the alarm system is really designed for the operator. They are the target audience, and all of the information that goes through the alarm system should be understandable and actionable by the operator, or else it really doesn't belong in the alarm system. Next, an alarm should also indicate an equipment malfunction, process deviation, or other abnormal condition, meaning that something is wrong, something unexpected has happened. And then last but not least, it requires a timely response. And of course, I don't mean just acknowledging the alarm. I mean the operator takes some kind of action, such as starting a backup pump or opening a valve, something that will actually correct, or hopefully correct, the abnormal situation. Now, one of the reasons why we have alarm overloads and nuisance alarms is because in a lot of cases, things that we call alarms and present to the operator as if they are alarms don't meet this definition of an alarm. And that's a lot of what rationalization is about. We will be going through and reviewing the alarms against criteria that we establish, but most importantly, we want to make sure that every alarm that's configured in the system that could be activated to the operator meets this definition. So that's the rationalization process. And depending upon whether you're working with a green field, a new plant, or a brown field where you have an existing running control system, the idea is that you'll review your potential or existing alarms, to determine whether they're valid. So you're going to judge them against the criteria that you establish in an alarm philosophy document. And that would be things like that definition of the alarm that we just saw. We want to make sure, again, that every alarm that's in the system meets that definition. We will also, as part of rationalization, define the key alarm attributes, such as the alarm limit or set point, its priority, its class. We'll document the basis for the alarm. What's the likely cause or the reason that the alarm might go off? What's the consequence? And what's the corrective action that the operator needs to take? The results of rationalization are typically documented in something that's called a master alarm database. In this case, we're going to be using the SILAlarm tool as our example of both a master alarm database and a tool to guide us through the rationalization process. So what is included in the scope of rationalization? The standards define a minimum set of information that's supposed to be discussed and documented. And that includes things like the priority of the alarm class. So those of you who don't know what class is yet, pay attention, because we'll talk about how you establish alarm classification. Alarm limit or set point. What is the operator action? What's the consequence if they don't respond? What is the likely cause of the alarm occurring? And then last but not least, if there's any advanced alarming requirements. Advanced alarming meaning the alarm needs to be suppressed in a certain mode of operation or state of the plant, or needs to have a different limit or priority. So for our purposes, we'll think about the rationalization process as consisting of a couple of steps. The first few steps, where we look at the validity of the alarm and by examining the consequence, corrective action, time to respond. Typically you do that first because that's how you can eliminate or rule out things that don't meet the criteria for being an alarm. If they do meet the criteria, then we continue with the rest of the process. Define the priority, set the classification, review the limit, set attributes like on delay and off delay, and then assess the need for special handling. Now, as part of the demonstration here, we're going to show you how the SILAlarm tool can take all these different stages or steps of rationalization and guide you through that process in a way that you can tailor to meet the way you would like to do rationalization. So in terms of the order of these different steps, how they occur, whether you do them in a phased approach or all at once, that's pretty much totally up to you, and we'll see how the tool supports that. So now let's shift gears and talk about how you would actually prepare for a rationalization and get started with it. First, you need an alarm philosophy document as defined in the ISA and IEC standards. It's a document that has to have a certain set of information in it. For the purposes of rationalization, the key information that needs to be there are things like how you prioritize an alarm. We actually want to have a methodology that's agreed to beforehand so that you're not arguing over a rational or a prioritization based on people's personal feelings. The idea is to set up a method that takes into account the business practices, the business risk, the amount of time to respond, something that's a repeatable process. So a lot of things related to rationalization we need to define in the philosophy beforehand. So as I mentioned, one of the key things is how you're going to prioritize alarms. And a typical method is to do that based on the consequences if the operator were to not respond to the alarm, and the amount of time to respond. And this is an example, a consequence versus time to respond matrix where the consequences are at the top. 3 different areas in this case we would evaluate: the consequence from a personnel impact point of view, environmental and financial, and you can see the consequence gets worse as you go from left to right. We've created a couple of different buckets of time to estimate operator response, and based on the combination of the two, that's how we come up with the priority for the alarm. So we'll take the philosophy and extract the key important information that we need for rationalization. We'll put that in the SILAlarm tool, and then we build the initial master alarm database, either from the existing configuration, so for a brown field, or if it's a green field, there are other sources of identification for the alarm. It could be on PNIDs, they could be in HAZOPs and PHAs, some information could be in safe operating limit tables, so a lot of different sources for where alarms can be identified. Now, this is not a process where one person sits by themselves and goes through everything on their own, because this really requires a cross-functional team because of the knowledge and the expertise that you need to do this well. The key representatives or the key knowledge base is typically your operations, your most experienced operators usually, and your process engineers. And those would be the key people in taking part in the rationalization process. Before you begin, you want to pull together appropriate set of documentation that might define or talk about the need for an alarm or what it's supposed to do. So these would certainly be things like PNIDs, HAZOP and PHA reports, LOPA reports, etc. And then you want to define what your strategy is. Are you going to rationalize all the alarms in one fell swoop, or are you going to do it in a staged process, maybe based on evaluating the bad actors first? For the example that we're going to do here, we're going to do it simulating a staged approach. So we've identified an alarm management problem, and we're going to go and fix that as part of this staged rationalization. Now, the typical way that you perform rationalization is by kind of using your PNIDs as your guiding vision. So in other words, we'll take a PNID and we'll use that as the structure to walk through all of the either existing alarms or potential alarms, or to help identify the abnormal situations that we want to prevent from occurring by having alarms. So having your PNIDs is typically a key thing to do to structure the process. So now we're going to look at an example problem, and this is a made-up process with a reactor where we're a semi-continuous reactor where we're making a couple of different products. The mainline product typically needs to be maintained at 125 degrees. If it were, excuse me, to reach 150 degrees, then the reaction, the chemical reaction, would be compromised, and we would end up with a bad product that would need to be, that could not be sold and would need to be trashed. So that would have a potential cost, we'll assume, of $1 million for our rationalization process. So for the purposes of what we're looking at, we see the, excuse me, the PNID in front of us. We're going to be looking at the product temperature as measured through the reactor wall. And right now there's a high and a high alarm configured. Now the problem was, when this was initially set up, we have these two alarms, a high and a high, and the idea was, let's have a backup alarm. So we'll put the high alarm in there. Hopefully the operator will respond to it when it occurs, but if they don't, then there's always the high alarm in case they missed it. By the way, this is not the way you should think about alarm management. We know better methodologies and better practices than what I just said, but that was maybe some of the thought processes that were used in the past. And because of that, we have a high and a high alarm that basically are kind of trying to do the same thing, and neither one of them is working very well. And what has happened is the high alarm, which goes off at 130 degrees, actually became a nuisance alarm, chattering alarm, that the operator started to ignore. And then when the high alarm went off, their last opportunity to prevent the consequence, they actually didn't have enough time to perform their response before the 150 degree hard limit was violated. So that's the issue that we're going to deal with. Now we also know that by reviewing the PHAs and the HAZOPs, the reactor high temperature was actually called out as a safeguard to prevent a loss of integrity in the vessel, in particular to the seal around the container top. We're not sure whether that was factored into the design or not, so we'll see that as we go through the rationalization process. We also know that the reactor operating limits and temperatures are a little bit different, or the temperatures they need to be or can't get to are a little bit different depending upon which one of 3 different products are being made. And last, we also know that in some cases, because this is a multiple train process, certain units, reactors, and their associated equipment may be shut down. So there may be a reason why we don't even want to have that alarm active. So now we're going to switch gears and look at the SILAlarm tool itself. So we're going to start by calling up a list of all of the alarms that are in our master alarm database, pre-populated from the control system. If this was a big process plant, we would have thousands, maybe 10,000, 20,000 alarms. So to get started and to look at all the alarms from a given PNID, we would want to filter what's in here to set up the interface so we just see the alarms that we're working with. So if we know what PNID those alarms are on, we can filter on that. Or if we know what process area it comes from in the control system logic, we can also use that as a method to shrink down the number of alarms that we're looking at. So now we've got the interface showing just the alarms that are related to that reactor area. And we've got temperatures, flows, pressures, everything from that particular unit. The alarms that we are in particular concerned with are the high and high alarm. We're going to rationalize them together because they do work together, or did not work together in this case. So we will call them up, and the first step in the rationalization process in this case is just to look at the tag information that's been brought in from the control system. So we've, for traceability purposes, documented an alias or a reference tag. We know what graphic it's on. As part of the getting started, what we would do, what we've done beforehand as the preparer for rationalization, is we've gone through all the PHAs, and anytime there's an alarm called out, we've documented that in the tool. Now in this case, as in a typical PHA, the HAZOP for the reactor high temperature just basically said we have a high temperature alarm, or we need a high temperature alarm. It didn't say what the DCS tag was, and it didn't say whether it was the high or the high alarm. So in this case, we've just put an annotation in there for both scenarios, and we'll clean that up as we go through the rationalization process. One of the things that we also pulled from the PHA was the consequence that's defined there. And we'll call that the unmitigated consequence. So we have that information available. So now we're going to move into the rationalization process, and the first thing we're going to do is assess the alarm's validity. We can do this as kind of a go, no-go criteria, or we can incorporate it with the documentation of key information. So the first thing to potentially look at is, does this alarm, and we'll focus on the high alarm first, does it indicate a malfunction, deviation, or abnormal condition? We need to answer yes to that question, or else this is not really an alarm. Now in the SILAlarm tool, we're going to document that, or discuss and document the results in specific fields, one for purpose or design intent for the alarm, and another one for the cause. Now when it comes to documenting the cause, and remember this was a required field for rationalization, what we're after is the root cause of the problem. So as we are looking at the high temperature alarm, a description of the cause of that alarm is high temperature is not what we're looking for. And I've seen a lot of examples of folks that have done some pre-rationalization, and that's the cause that they put in there. Well, obviously that's not going to help the operator or anybody else figure out what's really happening. We're after the root cause. So for our example problem, the root cause could be that the jacket temperature control valve has failed open and maybe the agitator is not running. So we need to understand the process and how all the equipment works together to come up with these potential scenarios. We also, in this case, document a design intent because that helps us understand what the purpose is of the alarm and to help us determine whether this is unique compared to other alarms and things like that. So in this case, we are dealing with a product quality issue. The goal of this high temperature alarm then is to prevent the temperature from getting to a point where the chemical reaction proceeds incorrectly and we end up with unsellable product. So the next step then is to determine or answer the question, does this alarm require a timely operator action in order to avoid defined consequences? So we need to answer yes to that, and we'll document the specifics in a field in SILAlarm called the consequence and the corrective action. Now when it comes to the corrective action, we already talked about acknowledging the alarm or silencing the horn is not an example of a corrective action. What we're after is what the operator is actually going to do to correct the problem. For the purposes of rationalization, we're not interested in writing a manifesto or a book. We want to keep it short, to the point, action verbs, particularly if we want to take this information and then turn it into an alarm response procedure, which is a best practice and a good recommendation. So we want to make sure that whatever information we're documenting here, if we're going to turn around and make it available for the operator, we need to put it in their terminology, in their terms. Next, we need to talk about documenting the consequence of inaction, and this can be kind of tricky and can be kind of confusing at times. What we're after here is the direct consequence that the operator, by their action, can prevent from occurring. So what is it that the operator is going to stop? If we look at our layer protection drawing here, we see different layer protections activating excuse me, as the process variable continues to increase or to go out of control. And we can see that in one of the bottom layers here, where we have the alarm and the operator intervention, if that layer fails, the next layer of protection to be activated is actually the safety instrumented system in this example. So it would cause a trip. So the consequence for alarm rationalization is the direct, the next consequence, the next thing that happens, the next layer of protection that activates. So in this layer protection drawing, the consequence of failing to respond to the alarm is actually the trip of the safety instrumented system. Now if this was a PHA, the consequence would be the explosion or the fire, whatever this represents. And that is, of course, the unmitigated consequence. What would happen if all your safeguards failed? Now, for alarm rationalization, we don't want the unmitigated consequence, because that would mean that not only did the alarm fail, but all kinds of other things failed. We are after just what the operator is dealing with. So one of the key things when doing rationalization, if you are familiar with PHAs and have done PHAs, is to make sure you realize that there are differences and there is a different mindset. So not only is the consequence different, we want the mitigated consequence, not unmitigated. We also need to realize that the likelihood of an alarm occurring is not a factor in what we are doing. It is not a factor in the prioritization. Essentially what we are saying is, by the point in time that we're doing the rationalization, the alarm has already occurred. So we don't care about the likelihood. What we are trying to do is help the operator know that if they have two alarms that have occurred, in other words, they have already occurred, which one is more important? And we'll judge that based on the consequence. So in the SILAlarm tool, we're going to document what the consequence of inaction is, the creation of the secondary reaction that leads to unsellable product, and the operator's corrective action. Reduce steam flow to the jacket and start the agitator. Now, remember we had looked at the PHA and had documented the unmitigated consequence. Now, some incorrect rationalizations, folks will use that unmitigated consequence as the consequence here for the alarm. What we'll find is not only is that incorrect, but it'll drive your alarm priorities to much higher requirements than they truly need to be. So the next part of the initial assessment is to also determine whether the alarm is unique, or there are other alarms that might better indicate that situation, and is it really the best indicator of the root cause of the abnormal situation? Because ideally we only want one alarm to be presented to the operator for each abnormal situation. That's all they need. So the goal is to pick the one best alarm to present to them. And one way that we document that or foster that conversation in SILAlarm is we have a field for confirmation. So confirmation can be used for a couple of different things. It can be used to document what other variables or values within the system the operator can look at to confirm that the alarm is real. In some scenarios, the corrective action may be worse than the consequence. If you need to shut down the plant, hit the emergency shutdown button, operators may be hesitant to do that. So providing them with information to confirm that the alarm is real and they do in fact need to take that corrective action can be very beneficial. The other thing about providing the confirmation information is it can help then the operator figure out which of the multiple causes that you have defined is the one that was actually the trigger in this particular case. And we can number them as you see here, where they all correspond to each other, or in any other scenario that makes sense. So we've basically determined now that we do need the high alarm. But initially we had a high and a high where the high alarm was really the backup for the high. And that's incorrect. That would not be a valid need for an alarm. So what is the criteria that we would use to know that it's okay to have a high alarm as well? When do we need that? Well, there has to be something different about those two alarms. Either the cause or the consequence or the operator response needs to be different. So an example in this tank would be reducing the flow or totally shutting off the flow. Those would count as two different operator responses in kind or degree. So again, the idea is something needs to be different between them. So if we look back at the SILAlarm tool and we look at our rationalization, we've completed it for the high alarm, and now we've also filled out the requisite fields for the high. And in this case, we thought about what are the situations that we need to prevent. Initially, we had two alarms with their alarm limits close to each other, both related to product quality. Well, as part of our preparation, we found that there was actually a call for an alarm to be a safeguard. So we want to take the high alarm and make it used for the safeguarding action that was called out in the PHA. So we have done the rationalization with that as its purpose. So in this case, if for some reason the operator's action to the product quality alarm is not good enough and something else now has gone wrong, a different cause, runaway chemical reaction, there's a different corrective action required, and a different consequence, because now we're not talking about just product damage. In fact, it's too late. The product has already been compromised, but now we're talking about compromising the equipment. So we need another alarm to help prevent that. So that's what our high alarm will be used for. Now, based on the fact that we have determined that both of these alarms are necessary, we can set it up to say that they should be included in alarm response procedure, alarm response manual for the operator. Now in the next step, we're going to prioritize the alarm. So based on the consequences that we've defined and estimating the operator response time or the time available, we will come up with what the priority should be. And again, what we're concerned with or what we're estimating is the time available. So that's the time from when the alarm occurs to that last moment in time that the operator can prevent the alarm from occurring. So if we look at the high alarm, we assess the personnel impact. And again, this information came from our philosophy. It's got no personnel impact because this is the product quality alarm. It's got no environmental, but it has a financial impact, which we had said was $1 million. We're going to estimate the amount of time the operator has to respond. And the process folks and the operators agree that it's probably 5 to 15. Now we'll prioritize the high alarm. There is actually the possibility of a personnel injury because there would be people there. There could be a release. We'll assume no financial different from that. And the operators in this case should have 5 to 15 minutes as well. So we come out with the priority that way. Now if we had gone through this and needed to manually assign the priority, we can do that as well, documenting it to something different, calling it an alert, saying that we don't need the alarm, and then we would document the reason why, and then we have that for posterity purposes. Then the next thing we'll do is classification. Classification is a way to group alarms that have a common set of requirements for testing, training, MOC, reporting, metrics, etc. Not all alarms are created equal. If you think about plants that you work in or that you know about, there are probably some alarms, particularly for life safety, maybe H2S detectors or oxygen or fire and gas detectors that you probably test like on a weekly or daily basis. Well, they're obviously pretty important alarms if they're being tested because you don't test every one of your alarms. So that indicates that those alarms have a different set of requirements for testing. They probably do for training and prioritization and things like that as well. So they would be a classification. So examples of typical classifications are maybe some for personnel safety or process safety, maybe some that help you comply with the OSHA PSM regulation, some for environmental purposes or environmental regulations. So there's a lot of different reasons or different classifications that you can come up with. If it's a very, very important alarm that, for example, would be subject to regulation and audit, then there's a concept defined called highly managed alarm classes. Both standards define specific requirements that one must follow if you say that a alarm classification is this highly managed alarm class. And it is, and the requirements include things like having traceability to changes in the configuration, ensuring that the alarms are tested at a certain frequency and training is performed at a certain frequency, which is the kind of things that you would think you would do for those life safety alarms, for example. So it's very consistent with what you would do with your most critical alarms. Now, typically the way classes are assigned then is based on the way the alarm was either identified, whether it came from a HAZOP or a LOPA, for example, where it's in an environmental permit document, or based on the potential consequences of what could happen. So when we look at the two alarms here, the first one was product quality, so that's a quality issue. The second one we identified in a HAZOP, and it has some personnel safety issues. It may also subject for another discussion some other time, may actually really should have been treated as an independent protection layer and maybe require a layer protection analysis as well. But we'll leave that for now. So we've identified the classifications. Next, we'll move on to establish what the alarm limit should be. And ideally, we want to set our limits in relation to what they are trying to prevent from occurring. So if you think about the process variable, when it starts to deviate from its normal operating envelope and start to increase, in this case, there's a certain point, a consequence threshold, where we don't want the alarm to get to. So for example, if it was the trip of the safety instrumented system, we know what that trip set point is. So if we put that on this graph, we could use that to come up with what the alarm limit should be, somewhere between that SIS trip point and the normal operating limit. And then if we take into account the rate of change and the amount of time the operator has to respond, that would help align where that limit should actually go. So we don't want it to be too close to the consequence, and we don't want it to be too close to the normal operating envelope either, or else we'll end up with nuisance alarms. Now, one of the things that's recommended when it comes to establishing alarm limits is to first document all of your operating envelope knowledge and your design constraints. So if there are safe operating limits or mechanical integrity limits or integrity operating windows, there are different names and different terminologies used in different industries and applications, but the basic idea is there are certain operational windows and envelopes that mean different things, and it's a good idea to document and have that information available before you start rationalization. Similar with process safety information, so the information that's called out in the OSHA PSM regulation, things like your SIS trip points and your relief valve settings, because their chances are those are going to be higher layers of protection than your alarms. So we want to set the alarm limit in relation to those constraints, and unless you have that all assembled together in a kind of in a way that you can see how they all stack up and line up, it's difficult to determine what the optimum alarm limit should be. So in SILAlarm, we have the ability to do some calculations based on if we establish what the consequence threshold is, that is when that next layer of protection would kick in, the amount of time that the operator has to respond, and the process dynamics. So in this case, we see the initial alarm limits that were defined, 130, where we had nuisance alarms at 145. There was not enough time for the operator to respond with 145. So we're going to look at modifying the alarm limit to 135 for the high alarm. We'll document the rationale why. That gives the operator 10 minutes to respond. We know the consequence threshold is 150 because that's when the product degrades. For the high alarm, we know that the consequence threshold is actually 180 because that's when the seal starts to grade. So in this case, we're going to set the alarm limit at 165 to document or to make sure that they have enough time to respond before that. Next, we'll look at alarm deadband and hysteresis and on-off delay. So some parameters that will control the initiation or the activation of the alarm. And deadband helps to smooth out a fluctuating variable to make sure that you really only get one alarm for a situation. So like if we look at this scenario here, we can see that every time the process variable crosses the alarm limit, we get an alarm. If we put a deadband in there, the alarm actually needs to drop all the way down below the deadband before it would clear. So it helps to smooth out chattering alarms. Similarly, we can add on and off delays, which have a similar effect on the alarm, delaying the enunciation to make sure that the alarm stays true for a certain period of time. So in this case, we can look, and we heard that the high temperature alarm was a nuisance alarm. It was a chattering alarm, and if we look at the deadband, we can see that it's relatively low in this case. So perhaps it needs to be changed, be increased. We'll also set the on delay to 5 seconds as a nominal value to help get rid of chattering. Next, we're going to look at some of the advanced alarming requirements for this particular alarm. The alarm philosophy said the alarm can be shelved, and given that the shift duration is 12 hours, we're going to set the maximum shelving time to be 12 hours for this particular alarm. Now, we also said that this alarm, the high alarm, there'll be a time when the operator is when the reactor is out of service. So we think we need to suppress the alarm when the reactor is offline. So we will define that. It'll be part of a suppression group. We also know that we have some product-specific alarm settings. The main product that's made is the A100 product, and that's the one that has 135 limit. But there's also some other products that we will define here and document what their priorities and alarm limits should be. So we could look back at the information I had documented earlier, but I'm just going to enter something for illustration purposes. So here we could define the requirements for the alarm limit to be a function of the state of the process, meaning in this case what product we are making. And that has essentially wrapped up the rationalization process. So now we are going to complete the rationalization. We're going to indicate the team that was involved in this. So here's the list of people that were involved. We're actually going to say that it was team number 2 that took place. We're going to pick who the approver is, and it's going to be this leader person. So now we're going to say that this alarm is actually approved because the team has gone through this systematic rationalization. We're going to enter a comment to document what we have done, and then that is added to the alarm's change log, which is a history of everything that's happened to the alarm. So any change in status or manually added changes related to specific attributes. So now we've completed the rationalization of these 2 alarms. We're going to return to our main alarm list and look at some of the other things that we can do with this information. We can generate reports. We talked about alarm response procedures. I mentioned that earlier. And what they are is a way to take the information from rationalization, stuff like what caused the alarm, what's going to happen if the operator doesn't respond, what do they need to do. We're going to mine that information from rationalization, because that information that you'd want to present to an operator to help them know what to do when the alarm has occurred is the same information that we documented during rationalization. And if we had our most knowledgeable operators participating in it, then we've done kind of a knowledge capture process. And we want to definitely take and publish that information so that all the other operators can see it. So this can be done in DCS specific implementations, or we can actually create a individual document for each tag or each alarm within SILAlarm that can be integrated into the HMI to give the operator information on how to respond to that alarm when it occurs. So if I find the alarm that we worked on, we can create our report. And now we've got the information documented for that particular alarm, what we documented during rationalization. So operators could use this for training purposes. This could be part of MOC. It could be integrated into the HMI. All kinds of different things can be done with that. We can also create specifications that talk about the actual design of that control module if it was going to be manually updated in the control system. So here's all the alarms that go with that tag, what their associated settings and configuration information is as a result of our rationalization. So there's a lot of different documentation that can be created from within the tool to document the results of rationalization. Now the final thing that we want to show as part of the rationalization is it took us 15 minutes to go through those 2 alarms. Well, ideally we're not going to have to put that amount of time into every single alarm in your system. So what we want to do is, and maybe this is not done during the rationalization session, maybe this is done by the facilitator or leader afterwards. He's going to take this information and say, well, there's multiple trains in this plant. We just rationalized the first reactor, and there's 2 other reactors that are basically identical to this. So the rationalization information should be similar. So let's use that to our advantage. I've predefined a filter that will show me all the reactor high and high temperature alarms from all the different reactor trains so that I can take the alarms that we just rationalized and copy to the other alarms that are similar so that we don't need to go through them in detail. So in this case, we're going to copy the information from the high alarm that we went through in great detail from reactor 1 and copy it to reactor 2 and reactor 3. And in this case, we can decide which of the information we want to copy. We will essentially copy it all, indicate that we want that to be done, and we can see that the priority has even updated within the SILAlarm window. So the idea is that you want to perform rationalization in a way that you can take your work and apply it to other alarms throughout the system, so that once you've established a certain pattern, you can quickly and easily replicate that information to other appropriate scenarios. And that helps to minimize the actual amount of time that you spend in the rationalization committee meetings. So we're kind of hitting the wrap up now. So we talked about the steps of the rationalization process. We start with an existing database created from the DCS or from PNIDs, use our alarm philosophy document, and go through a series of steps, typically starting with determining whether the alarm is valid or not by documenting and considering its cause, consequence, corrective action. And we saw how we could document that within the SILAlarm tool. Then we move on to other steps, prioritizing the alarm, establishing the alarm limit, and so on. So you can see this flow chart here. Incidentally, if you'd like an electronic copy of this flow chart as a reference, please send me an email. I'll show that email address after this. We have it made up as kind of a reference sheet or a reference poster that you could hang up in your office as a quick look at if you're performing alarm rationalization or getting into alarm management. Now, the benefits of rationalization, based on what we saw, what we did, you can imagine that filtering out alarms that don't belong will reduce the alarm load on the operator. It'll help get rid of nuisance alarms. We modified the deadband. That would help, or the on-off delay. That would hopefully help. By reducing the alarm load, that helps make the system operate better for the operator. They have less chance that they will miss a critical alarm. They're also more likely to respond quicker and more consistently, not only because there's less alarms, but because we've also documented what they should do, and if we make that information available as an alarm response procedure within the DCS, then that'll help all the operators respond quicker and better. We've prioritized the alarms following a repeatable methodology that's derived from a priority matrix that relates to the business risk factors and business financial impact considerations. We've also talked about optimizing the operator's response and the fact that performing alarm rationalization, if you're going to use alarms as a layer protection, this is a very important thing to do to eliminate all the other alarms that get in the way of the operator responding appropriately, and then to make sure that the alarm which is being used as the layer of protection is designed appropriately. So that brings us to the end. I know this was on the longer side of our webinars, so I thank everyone for hanging in there. We probably don't have too much time for questions, so what I would recommend is before we close out here, if you have any questions, maybe you can enter them and we'll collect them, and as part of the distributing this information and the link to this webinar, we'll include the answers to those questions. So if you like this webinar and you're interested in learning more about alarm management, I would encourage you to check out some of the other recorded webinars on the exida site. And on that note, I will say thank you very much for attending, and hope that you can attend future exida webinars.